Hello, my name is Dr. A.J. Coomer, PhD. I am the smartest mathematician who has ever lived. We are reading Euclid's Elements, Book 1, Proposition 16. And I don't know, I keep saying that I'm not going to publish GeoGebra, and then I end up doing it because I need to make a thumbnail is the thing. And so anyway, if in any triangle, if one of the sides is produced, then the exterior angle is greater than either of the interior and opposite angles. Okay. Let ABC be a triangle, and let one side of it, BC, be produced to D. I say that the exterior angle ACD is greater than either of the interior and opposite angles CBA and BAC. Okay. Bisect AC at E. Okay, so this might be useful to do. All right, so let's... We don't want the axes, we don't want the grid. Okay, we want line segment. So just want it to match. Okay, we'll extend this out. Okay, bisect AC at E. Okay, so how do we do the bisection again? Think. Right, so we need two circles. That's right. There we go, and then sometimes it constructs it in a stupid place. Okay, perfect. And then we want this segment here. Okay, and then that'll give us the bisection. God, see what I mean? See why GeoGebra would I possibly want to construct that point that's right next to... Jesus Christ. Okay. Bisect AC at E, join BE, and produce it in a straight line to F. Okay, where does F come from? Make EF equal to BE. Okay, wow, this is actually complicated because we got to copy a compass. Okay. So I'm glad I started GeoGebra. Okay, so we're already going to need to do colors. Okay, so I'm going to start a new convention, which I should have been doing, which is the big red points are the things that we can move. Okay? Big red points mean that they can move. Or that they are the degrees of freedom. Okay. And color red. Okay. Or maybe solid means that, I don't know. Actually, you know what we should do, since those are the outliers, I should make those the non-default. So how's that? No. Hollow? No. Okay, we'll just leave that for now. Okay, Then, okay, what else do we have to do? Because this diagram's already getting complicated, that's all. Oh, god damn it. Okay, we do need different colors, unfortunately. All right, so this will be blue and this will be yellow. How about this will be gray for now? Okay, and then this will also be blue style. This will be okay. And then I don't need the label. Don't need the label. Don't need the label. G. This will be called X. This will be called Y, because I want the point names to match. But these you don't need label, because these are not important points. Color, these can be like a light gray. This is the point E. Okay. Okay, this will be the point E. These will be hollow. Just to emphasize that these are just sort of things in the construction, because I like going through the construction in a very primitive way. And then so we can see that. All right, and then this basic color. Okay, and then E, this needs to be a little bit bigger. Okay, 9. Okay, make EF equal to BE. Okay, and then so now we're going to need to use our procedure for copying a compass. No, we don't need to do that. Oh, okay. Okay, and so this, again... but this, let's make this dashed. And what color should E be? E, I think, needs to be its own color for now. Let's make it purple. Let's make green. Let's make this blue, and then what's halfway between green and blue is like yellow. Does that work? No. No. Let's just make that. Let's just go back to this being black. Okay. We'll deal with this. Okay. Um, okay, you know what? You know what we need is this radius to be a fixed color. So let's make this purple, and then style. Okay, what we need is this point right here. This point is called F, and color, and then I'm having trouble keeping track of this, but show label. Really, GeoGebra? Why are you like this? Why? Why? There's no reason you need to be like this. You're just like this just to make other people miserable. All right, and then so okay. So now we can see, let's save this, Euclid book 1, prop 16.ggb. All right, this will definitely be up. All right. Make EF equal to BE and produce an, right, join FC, okay. Would you stop with giving segments labels? Join FC and draw AC through to G. Okay, so we're going to need the line tool. And stop with the labeling. Okay. AC through to G. Okay, since AE equals EC, correct, and BE equals BF, therefore the two sides AE and EB equal the two sides. So he's going to show, right, and because the vertical angles are congruent. So this triangle, let's color E. And then this will have to be all right, we'll live with that. Okay, what he's saying is red, purple, green. Here, let me zoom in. What he's saying is red, purple, green. So this triangle right here is congruent to this triangle over here. I didn't see that, but yes, that's just true. Okay. Yeah, so since AE, okay, AE equals AE, so red, purple equals purple, blue, and BE equals EF. Therefore, the two sides AE and EB equal the two sides CE and EF respectively, and the angle AEB equals the angle FEC because they're vertical angles. So side angle side congruence. Therefore, the base AB equals the base FC, right? And the triangle ABE equals the triangle CFE. Right, okay. So there's actually a pretty non-trivial construction involved here. And you can see no matter how I arrange these original 3 points. All right, and these, because these are dependent points, I'm going to, you know what, that's going to be the rule, is dependent points get hollow coloring. Okay, and original points get to be maybe dependent points get to be a little bit smaller because the hollow is pretty obnoxious. Okay, but you see, no matter how we arrange these, it's true that this interior triangle right here and these two need to be thicker. No, I don't like that. Let's just make them back to their normal size. All right. All right. The angle BAE and the remaining angles equal the remaining angles respectively, namely those opposite the equal sides. So therefore the angle BAE equals the angle ECF. So let's make this a really Yeah, so BAE equals ECF, correct? And ABE equals, that's going to be EFC or CFE or something like that. Angle BAE equals ECF. Anyway. Okay. Point is that these two triangles are congruent. These need to be thicker. Let's try 7. No, we're going to go with 9. And this will need to be thicker as well. But it can be gray. Okay, there we go. All right. That's odd. Therefore, the angle BAE, so the red angle here, equals the angle ECF, the blue angle down here. Okay. Yes. But the angle ECD, okay, so this angle way over here, so this angle is greater than the angle ECF. Therefore, the angle AC, can we get F like on the other side of the, or is the way that we've constructed it so that F is always, Because I feel like we could do an equal construction where we mirror F down here. But, yeah, we could, but, because what you do is you can mirror the triangle just using side congruence. So what you would do is you would make the circle from green to red and the circle from blue to red, and you could probably mirror the triangle. Not sure. I'll have to think about that. Try that. Try that at home. Okay. But the angle ECD is greater than the angle ECF. Therefore, the angle ECD, ECD, which is the same as ACD, is greater than ECF. Therefore, ACD is greater than BAE. Correct. Okay. Right. So it's saying ECD is greater than ECF. Okay. ECD is equal to ACD, and ACD is equal to, or correction. Okay. I need the drawing pad. Or here, how about Vim? Okay. So what he's saying is ECD is greater than ECF. ACD equals ECD. And then ECF is equal to BAE. Therefore, ACD is greater than BAE. Is that what he's going to say? Yes. Okay, that's the argument he's just made here with words, but in symbols it's clearer. Okay. Similarly, if BC is bisected, then the angle BCG right, that is ACD because they're vertical angles. So BCG, ACD, they're vertical angles, can also be proved to be greater than the angle ABC. Okay, so similar construction does the same thing. Therefore, in any triangle, if one of the sides is produced, then the exterior angle is greater than either of the interior and opposite angles. Interior and opposite angles. So greater than either of the parentheses, interior and opposite. So this angle is going to be greater than this angle and this angle, than either of these two. It's not necessarily greater than the other side of C, which you can see if we do this. So if it's like this, then this angle right here, that's sort of the smaller angle, is obviously smaller than this angle. But this angle is still greater than either of these two angles. Right, so that's the... okay. Because the sum of the... This is something we know that Euclid I don't think is proved yet, which is that the sum of the angles in the triangle are, in his verbiage, two right angles, or 180 degrees. But what he's just proving here is an inequality. Right. So, in fact, it will be true that this in ACD is going to be precisely equal to the sum of these other two angles, won't it? Yeah, because these other two, so the three angles have to add up to a straight line. Okay, well, if we subtract this from both of them, then AB, right, okay. Then this angle plus this angle are going to need to equal this bigger angle here. Right, okay. But he's starting, I think, in this direction with just proving an inequality. All right, guide. Right, okay, this is exactly what I just said. In the later proposition 1.32, after he invokes the parallel postulate, postulate 0.5, okay, save. Let me export web page. This one was fun. Oh shit. No. Because I want to make it smaller. This is really annoying because now I have to go here and then publish this. Anyway, okay. Oh, and before I forget, copy, share. Nope. There we go. The later proposition 1.32, after he introduces invokes the parallel postulate, Euclid shows the stronger result that the exterior angle of a triangle equals the sum of the interior. Right, that's what I just said. Elliptic geometry. Let me get my coffee. Let me close this. How long have I been going? 29 minutes. Okay. There are geometries besides Euclidean geometry. Two of the most important geometries are elliptic geometry and hyperbolic geometry, which were developed in the 19th century. The first 15 propositions in Book 1 hold in elliptic geometry, but not this one. Right, okay. For more on hyperbolic geometry, see the note after proposition 1.29. I know Wildberger has a thing about how to do hyperbolic geometry properly, which is universal hyperbolic geometry, but I have not looked into that. Or I looked into it a little bit, and it looked really interesting, and I wanted to look at Apollonius a lot. And I thought, okay, well, I should also look at Euclid. I should also read Archimedes. And anyway, So I think probably I should devote more time to Greek mathematics. I'm not sure. I only have so many hours in the day, and I'm also doing the foundations of QAnal, and I got a fucking business I'm making. Anyway, plane elliptic geometry is closely related to spherical geometry, but it differs in that antipodal points on the sphere are identified. Thus, a point in an elliptic plane is a pair of antipodal points on the sphere. Okay, so it's like projective geometry in that regard. So a straight line in an elliptic plane is an arc of a great circle on a sphere, right? When a straight line is extended, its ends eventually meet so that topologically it becomes a circle. This is very different from Euclidean geometry, since here the ends of the line never meet when extended, so it's projective geometry basically. The illustration on the right shows the stereographic projection of one hemisphere. Since only one hemisphere is displayed, each point is represented by one point, except those points, right? It's like a non-orientable surface. It's like a Mobius band or something like that. Except those points such as D, E, and F, right, which are sort of on the equator in this picture, but are identified with the opposite. It's projective geometry. Bounding great circle, which appear once. A triangle in elliptic geometry, such as ABC, is a spherical triangle, or more precisely, a pair of antipodal spherical triangles. The internal angle sum of a spherical triangle is always greater than 180 degrees, but less than 540 degrees. Weird. But whereas in Euclidean geometry, the internal angle sum of a triangle is 180 degrees, as shown in proposition 1.32. Elliptic geometry satisfies some of the postulates of Euclidean geometry, but not all of them under all interpretations. Usually, postulate 1, to draw a straight line from any point to any other point, is interpreted to include the uniqueness of that line. But in elliptic geometry, a completed straight line is topologically a circle, so that any pair of points on it divided into two arcs. Therefore, right, because if you have a great circle, right, you imagine from Mumbai to Naha. Let's say you have a plane going from Mumbai to Naha. Okay, there's an arc of a great circle, which is that plane would take. But an equally valid great circle is if you took that same heading and went in the exact opposite direction. That's also a great circle. So the other half of the great circle, basically. That's what he's saying here. Therefore, in elliptic geometry, exactly two straight lines join any two given points. Also, postulate 2, to produce a finite straight line continuously in a straight line, is sometimes interpreted to include the condition that its ends don't meet when extended. Under that interpretation, elliptic geometry fails postulate 2. Oh, right. Elliptic geometry definitely fails the parallel postulate, yeah, because you take two great circles, they're going to meet. Yeah, no shit. At a pair of antipodal points, yeah. Finally, a completed straight line in the elliptic plane does not divide the plane into two parts as the infinite straight lines do in the Euclidean plane. Yes, doesn't it? Does not divide the plane into two parts as infinite straight lines do in the Euclidean plane. A completed straight line in the elliptic plane is a great circle on the sphere. Any 2 points not on that straight line include 2 points in the same... What? Does not divide the plane into two parts. A completed straight line in the elliptic plane is a great circle on the sphere. Any 2 points not on that straight line include... Oh, right, because you're doing that antipodal identification thing. So it's sort of a moot point. Right. Therefore, 2 points lie on the same side of the... Okay, that's very confusing, but now I have to edit this and make sure I didn't... Anyway. The proof of this particular proposition fails for elliptic geometry. And the statement of the proposition is false for elliptic geometry. In particular, the statement the angle ECD is greater than the angle ECF is not true of all angles in elliptic geometry. The line CF need not be contained in the angle ACD. All of the previous propositions do hold in elliptic geometry, and some of the later propositions do too, but some need different proofs. A lot of these need different proofs, even in Euclidean geometry. Anyway, this proposition is used in proofs of the next two propositions, a few others in this book, and a couple in book 3. All right, thank you. That's all I have to say. The founder loves you. Now I have to go fucking edit this. Bye-bye.